Hello and welcome to Orbital Mechanics 101. Today we're going to talk about the basics that you need to know about orbital mechanics in order to plan missions to other planets and elsewhere in the solar system. We're going to start off by talking about what an orbit is and the different types of orbits. Then we'll move on to how to actually get your rocket into orbit. Finally, we'll talk about how you can change your orbit, and as an added bonus in part 2, we're going to actually plan a mission to Mars. And let's say this is a planet. And what you do, let's say you have a cannon on the top of the planet, and then you fire a cannonball out of it. It'll fly, say, a few kilometers before hitting the ground. But let's imagine that you have a very powerful cannon, and this one can fire tens of kilometers. But it still hits the ground. But then imagine that you have a super powerful cannon that can fire hundreds or thousands of kilometers. And what you'll find is that actually, once it takes off, the surface of the Earth will actually curve going. All of the time, it's falling towards the center of the planet, but it never hits the surface because the surface keeps curving away beneath it. And this is why astronauts on the International Space Station float, because they are actually falling cut. So we've just seen one type of orbit, a circular orbit, which is what I just demonstrated. But that's just one of 4 different types of orbit that exist all throughout the universe. A circular orbit is like this. At the centre, we have an object, usually the Sun in the case of the solar system, and then around the object, we have a planet going around like this. And a circular orbit means that there's always a constant distance between the centre and the object that's going around. But more generally, we have objects that actually get closer to the Sun and then further out, and we call these elliptical orbits. Now, the parameter of interest for an elliptical orbit is called the semi-major axis, because, for example, if we look at a circular orbit, there is a constant distance between the centre and the actual planet, and we usually call that r. For an elliptical orbit, you can see that it's constantly changing all the time. So what we do is we get this distance here, we add this distance here, and we call that 2 times the semi-major axis. This point here, which is the closest point to the Sun, we call the periaps. And this point here, which is the furthest from the Sun, is called the apoaps. But there's also 2 other types of orbit that exist in the universe, but usually these aren't mentioned that much. These 2 are so-called unbound orbits. This case is called a parabolic orbit. This is, for example, in an orbit that a comet coming from the outer solar system might follow, where it flies by the Sun really, really, really fast, and then it flies out and it never comes back ever again. So very unlike the planets that go around the Sun and keep going back around over and over and over again. And if you have even more energy, then you get something called a hyperbolic orbit, which again just comes in once and then never returns. So these are the 4 types of orbit, and in general what we're interested in is this kind, the second type, elliptical orbits. And in fact, one of the most important laws in orbital mechanics is called Kepler's first law. Follow an orbit around the Sun that is elliptical in shape, with the Sun, which is here, at what's called one of the focuses of the ellipse. So, great. Let's demonstrate another thing that's actually useful, because this is just a picture at the moment. There's one other thing that's really useful if you want to quickly get an idea of how long it takes an object to actually go around the Sun. And this is called Kepler's third law, which we're going to use a few times, which is really, really simple. I'll just write it out here. Kepler's third law states that the time it takes for a planet to go around the Sun, which we're going to note by P for the period, squared, is equal to the semi-major axis, this little a that we have up here, cubed. This here is measured in years, and this here is measured in astronomical units, where this is the distance between the Earth and the Sun. So as a quick example of this, the semi-major axis of Mars's orbit about the Sun, so for Mars, A is equal to 1.52366 astronomical units, which means that Mars is about 1.5 times further away from the Sun than the Earth is. And if we plug this into this equation, it tells us that the period, or how long it takes Mars to go around the Sun, is 1.88 years. So just short of 2 years, or 687 days. So great, we've already got one result and we haven't even really started yet. So in order to get a handle on dealing with problems in orbital mechanics, there's one really important thing that comes up all the time, and that is conservation, quantities that stay the same in time. So in order to investigate this, let's go back and take a look with an experiment. To see our first conserved quantity, let's take an object. This monkey will do, I suppose. And what I'm going to do is I'm going to raise its height, and in doing so, give it something called gravitational potential energy. And then when I let go of this object, it falls. The energy, gravitational potential energy, has transformed into another type of energy, called kinetic energy, or the energy of motion. But the sum of the gravitational potential energy plus the kinetic energy is always a constant. Energy cannot be created or destroyed. In terms of orbits, what we say is that the energy, which we write as E, is given by the sum of a kinetic energy term, the expression given by a half mv squared, where this is the mass of, say, your rocket or your planet, whatever is going around the Sun, and this is its velocity or its speed. And then we have a potential energy term, which is given by g, Newton's gravitational constant, times by the mass of the object, times by this large m here, which is the mass of the object in the centre, the Sun in this case, but it could be the mass of, say, the Earth, in the case of a satellite going around it, divided by the distance between the object at the centre and where you are in your orbit. And this E here is always a constant, unless, for example, you fire your engine or something. So that's one of the two really important conserved quantities. Now let's have a quick demonstration of the second one. Our second conserved quantity is called angular momentum. So to demonstrate this, I'm going to take an object, in this case just a memory stick, and start it in rotational motion. So notice that I'm spinning it, but it's spinning quite slowly. Now what I'm going to do is decrease the distance from the centre that it's rotating at. Notice that towards the end it suddenly speeds up, and this is at the heart of conservation of angular momentum, which states that the mass, in this case the object at the end, multiplied by the distance to the centre times by the velocity that it's rotating at is always a constant. So that means that once it gets closer to the centre and the distance becomes smaller, the velocity has to increase, and that is angular momentum. Great, so let's take a look at the expression for angular momentum, which is a lot simpler than one for energy. Usually we use the letter L for angular momentum, and that's given by the mass of the object going around the orbit, times by the distance away from the centre, times by its velocity. And in general you would get a factor of sine of theta or something in there if you were being more pedantic, but this will be fine for us when we're talking about circular orbits. So this L here, the angular momentum, and this E here, the energy, will always be constant unless you fire your engine or, say, put more energy into the system. So let's take a look at what this equation actually means. So let's imagine that we have the Sun at the centre, and then a comet is going around an elliptical orbit like this. So here is our comet with its nice little tail. I don't know, comet 67P or something. Right, so when the comet is here, this r is really, really small because it's really close to the sun. When this r is small, this quantity here becomes very, very large. And the only way that E, which is just a number, say it's 5 or it's 7, can stay a constant if this becomes really, really, really big, is for this quantity, the kinetic energy, to also become really big. And so that means that this V here, which is the only thing that can increase here because the mass is a constant, has to go up. So what this means, in layman's terms, is that when you get closer to the sun, you go faster. So comets go really fast when they're close to the sun, and when they're really far away from the sun, they go slow. And the reason for that is all hidden inside this one equation, the conservation of energy. So now that we've got our equations, now let's move on and take a look at the next step, which is how do you actually get into orbit? Firstly, let's work out if you had a rocket and you fire it straight upwards with some velocity v, how large does this velocity have to be in order to completely escape from the Earth such that you won't fall back down? And this is called the escape velocity. So firstly, our rocket is sat on the surface of the Earth, and its initial velocity is v, so its energy to begin with, E on the surface, will be given by the kinetic energy, which depends on the velocity it's launched at, minus the potential energy, G, times by the mass of the rocket, times by, this is the mass of the Earth in this case, because we're launching from the Earth, divided by, and in this case, r is the distance from the centre of the Earth to the surface, the radius of the Earth. So this is the energy at the beginning, and because of conservation of energy, this will also be the energy when it escapes all the way to infinity, which I'm going to denote by E infinity. This is the symbol for infinity. So what will this be equal to at an infinite distance away? Well, this r will be very, very, very large, which means this term will rapidly go towards 0. So we'll have a 0 for the potential energy. And because we're talking about the velocity you would need to only just escape to infinity, it means you'll slow down and slow down and slow down until eventually your velocity is completely 0 when you reach infinity. So the kinetic energy will also be 0. So we have 0 plus 0, so this E infinity here will just be equal to 0. So now, if we want to actually get the velocity, we can rearrange the equation, a half mv squared minus gm times the mass of the Earth over the radius of the Earth is equal to 0, to get that the escape velocity will be given by the square root of 2 times by g times by the mass of the Earth divided by the radius of the Earth. So this is how fast you have to launch a rocket to escape all the way to infinite distance. And how big is this? So we can actually plug in numbers. So g is given by 6.67 times by 10 to the minus 11, and then the units are just meters cubed per kilogram per second squared, but that doesn't really matter that much. The mass of the Earth is given by 1.988 times by 10 to the 30 kilograms. And in fact, actually, ignore that. That's the mass of the Sun. The mass of the Earth is actually 5.972 times by 10 to the power of 24 kilograms. And the radius of the Earth is equal to 6,371 kilometers, which tells us that the escape velocity is equal to 11.2 kilometers per second, which is very fast, and hence why it's so hard to actually get a rocket to escape from the Earth. But let's think about one other thing we could do with this second rocket, which I put on the other side of the Earth. What if, instead of going straight up, we go up and then curve round until we're actually going in a circle just like in the demonstration I showed you, where I was swinging an object around my head. In this case, our rocket is going around a circle with a different velocity v. I'll call it vc for v circular. And like I mentioned, there has to be a force towards the centre in order to keep it going round in a circle, which is called the centripetal force, or the centre-seeking force. In this case, the only force acting towards the centre is the gravitational force. So what we'll have is the centripetal force, which in general is given by the equation the mass of the object times by the circular velocity squared divided by the distance to the centre, so that the distance from here to the centre of the Earth. This is the equation for the centripetal velocity, and this will be equal to the force of gravity, which is providing that force, which is given by Newton's gravitational force equation. G times by the mass of the rocket times by the mass of the Earth in this case, divided by the distance squared. So if we equate this to this and rearrange the equation to get what Vc is, we find that the circular velocity, if we cancel the m's, multiply by the r and take the square root, is given by the square root of g times by the mass of the Earth divided by the distance from the centre of the Earth to the rocket. So how large is this? So let's imagine that this rocket is the International Space Station, for example. In that case, the International Space Station orbits at around 400 kilometres or so. So in this case, the relevant r will be the distance from the centre of the Earth to the surface, plus 431, which is how high the International Space Station is, which is 6,802 kilometres. And we plug in the mass of the Earth and g from before, and that tells us that the circular velocity is given by 7.65 kilometres per second. And note that this is smaller than the velocity to escape from the Earth entirely, so it's much easier to get into a circular orbit around a planet or star than it is to get all the way to infinity. Okay, great, so we've managed to reach orbit around the Earth here. Now let's talk about how you can actually change your orbit, because we've talked about conservation of energy and conservation of angular momentum, which is the reason why once you start on an orbit, you always go back to the same point. But if we want to get somewhere like the Moon, we're going to have to be able to change our orbit. And the way we do that is by putting energy into the system by firing our engine. So let's say that we have a rocket here going around the Earth, and then we fire our engine here with some little bit of velocity, which we call it a delta v, delta meaning change in velocity, and we do it in the direction that we're going around the Earth. Because we're going a little bit faster, we're going to move slightly further out like this, and if we put enough delta v in, we can actually go all the way out to here, but then all we've done is changed our circular orbit into an elliptical orbit, so then we would fall back down and go back to where we came from. So in this case, we've changed a circular orbit into an elliptical orbit, and notice that it changes the orbit 180 degrees away from where we actually fired it. In fact, we go back to exactly where we came from. And if we want to actually get captured by the Moon, or you could use this to get to Mars, for example, we need to fire our velocity at the opposite point of the orbit, give it a different delta v. This will then raise the orbit at the opposite end and convert our new elliptical orbit, called an elliptical transfer orbit, into a new circular orbit at the distance from the Earth that the Moon is at. So this process of firing your engine once to go into a transfer ellipse and then firing again to go into a circular orbit is called the Hoffman transfer. And in part 2, we're going to be using this in order to plan a mission to Mars.
Thanks for watching. Did you find this video useful, or do you have any burning questions about orbital mechanics? Let me know in the comments below. There's a new interview with Mars One CEO Baz Lansdorp out this week, which you can check out over there on the right, along with a TV appearance I made with him earlier this year. Part 2 of this video comes out in a fortnight, but before that I've got the latest Mars One news in this month's mission update coming out on Tuesday. And until then, I'll see you next time.